Buenas noches, good evening, everybody. Welcome to day one on week 10 of the semester. In today's class, we are going to finish the concepts of chapter 6, which we are dealing in this chapter with carbohydrates. Last class where we ended was specifically talking about the most common monosaccharides that exist in nature, or that some of these common monosaccharides, because galactose is an exception, but I will re-mention it again. And you can see that the three common monosaccharides that are out there, and understand that there's more monosaccharides. These are just the most common, are glucose, fructose, and galactose, okay? You can see the structures for glucose, fructose, and galactose. You can see it to the right side there in order of first glucose, then galactose, then fructose. So when it comes to these monosaccharides, you can see that in terms of structures, they are all hexoses because they have 6 carbons in their structures. Now, glucose and galactose are aldohexoses because they have an aldehyde motif in their structure. On the other hand, fructose is a ketohexose because instead of having an aldehyde, it's going to have a ketone structure in them. Now, understand that in this class, since the class is online, you guys don't have to memorize these structures per se, but it is important that you know how to classify monosaccharides depending on their aldehyde functionality and depending on the number of carbons. And that is something that we practiced in class last time. Now, in today's class, the first thing that we're going to understand are the reactions of monosaccharides. This is important to know because monosaccharides can undergo a series of reactions in order for them to make new products or to actually rearrange and make a structure that at least looks a little bit different. So in the first reaction that we have for monosaccharide, this reaction specifically is a cyclization reaction. So the reason why this is a cyclization reaction is because we're going from an open form, from that Fischer projection in our monosaccharide, to its cyclic form, okay? So when we look at the images, I'm going to zoom in to look at all of these. Oh, before I continue, I was thinking over the weekend, and please let me know if this is something that will benefit any of you out there. I understand that in chapter 5, which part of it is going to be in exam number 3, when it comes to reactions, it may be a little bit confusing on how do I predict the product of a reaction, or how do I know if it's condensation or if it's a hydrolysis reaction. I want to make a specific handout for you guys, and put a 2 in the chat if this will benefit you, in which is going to outline, hey, these are the condensation reactions that you guys should know. And this is the functional groups in the reactants, and this is the functional group in the products. Also for hydrolysis reactions, hey, these are the functional groups that can get hydrolyzed, and this is going to be the functional groups that are produced from the hydrolysis. Because I want you guys that at least are, when it comes to that in exam 3, that you guys have at least a handout that will be able to outline and you have a reference to in order for you to study that concept. Because it is my understanding that when it comes to the textbook, there's not a lot of practice problems on it. And I gave you some in the in-class worksheet, but I want you guys to have like a formal handout in order for you to have like a physical copy of like, oh, okay, if I know that I have a reaction question in my exam 3, I can go to this handout and sort through the reactions via looking at, oh, okay, these two functional groups will make via a condensation reaction this functional group. Awesome. Great. So I will be preparing that by the end of this week, and I will let you know when that post, so you guys will have it there. I know that last time you guys requested also to look at a video when it comes to addition reactions, and in the Canvas for the course, I actually put my lecture from some time ago. Understand that when it comes to the addition reaction, the hydration reaction, the explanation that I give there is a little bit more in depth because there are different kinds of alkenes, and then sometimes you have to pay attention to the hydrogens. So understand that in this course particularly, what you are concerned with is understanding I need to have one carbon atom that has more hydrogens than the other. The other alkenes, you guys don't have to be concerned with because I didn't explain it in class. And I think it's unfair to test you on that when we didn't discuss it in class. So make sure that if you use that as a resource, even though the discussion on addition reactions, specifically on hydration, is a little bit more extensive, focus only on how do I add hydrogen and OH to an alkene when one carbon has more hydrogens than the other, okay? Okay, so going back to the cyclization reaction. So here we have the molecule of glucose, okay? We can see that glucose has, as we mentioned before, this area of the molecule, which this is an aldehyde. And then we know that in the rest of the molecule of glucose, we're going to have a series of hydroxy groups. And we can see those hydroxyl groups right here. We have 1, 2, 3, 4, 5 hydroxyl groups. Now, understand that having hydroxyl groups nearby an aldehyde, we can actually do a cyclization reaction. In this cyclization reaction that is happening right here is called an aldol reaction. Okay? And in this aldol reaction, all we're doing is combining the aldehyde, that's why the ALDO in the reaction, and then the OL from the alcohol. That's why it's called aldol. Now, not every single hydroxyl group in a monosaccharide will be able to undergo cyclization, okay? The OH that determines the D and L notation in your monosaccharide is the one that is undergoing the cyclization. So if I number my OHs as 1, 2, 3, 4, and 5, and if we are guided by that Fisher projection in the cyclic form, okay, which OH, in the way that I number them, is the one that is reacting with the carbon and the carbonyl for the aldehyde. Let's put it in the chat. Which OH is the one that is involved in the reaction? I see that people are putting 1. I don't see. Let me label this. Let me label in the product. Make it more. So the only person that Caught it was Maria. Put a 2 in the chat if now it makes sense that the 4th hydroxyl is the one that undergoes the cyclization. No problem. So we can see here, if we zoom in into the molecule, that we are going to have the different OHs. That should be clear, okay? So OHs can actually react with aldehydes via the aldol reaction. Now, the reasoning behind why is it that that OH specifically is the one that reacts with the carbon in the aldehyde, which if I highlight, where's the aldehyde? Because we don't see it in the product, of course. This is where the aldehyde used to be. Okay. Overall, is because when that cyclization happens, we can form a 6-member ring. And the stability of a 6-member ring is really high. The reasoning why the stability of a 6-member ring is really high is because each of those carbon atoms is tetrahedral, and 6-member rings can actually bend. And in that bending, they can adopt an angle that is really close to that of 109.5 that the carbons like to sit in. Any of the other OHs there will make ring systems that are going to be a little bit more strained, meaning that their angles are not going to be that ideal, 109.5. So that's why specifically in this reaction, the OH that determines the D configuration, which means, remember, D means that the OH in the chiral carbon that is the farthest away from the aldehyde is pointing to the right, okay? So remember, the D is because of this carbon atom. The OH is pointing to the right, so that's why this is D, glucose. So taking that into consideration, then we know that in this reaction, this is the way that is going to react always, 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 always. So again, the carbon that determines the DOR notation, the OH on it is the one that is going to undergo the cyclization. So here I also give you what does the molecule look like at the end. Okay, but I want to give you guys the steps of how we actually come up with that as our last structure. Understand that the molecule that we have here, this is called a Fischer projection. And then the molecule that we have here, which is the cyclic version of my monosaccharide, that is called the Haworth projection. Okay, so the Fischer looks, students always tell me that the Fischer projection looks like a fish where the spines is what you see, but then the Haworth is going to be like a donut because it is cyclic. I don't know if that helps anybody. I'm just putting it out there because I've heard it from students in previous semesters, okay? Now, how is it that we can transform from a monosaccharide to a cyclic monosaccharide? Well, these are the steps of how we draw this, okay? So let me continue labeling the molecule similar to what I have in my Fischer projection, so at least you guys can keep track of this. So my aldehyde is right here. okay? And then we can see specifically that this also illustrates how we form the Haworth projection for glucose, okay? So the OH that is going to react with the carbon in the carbonyl of the aldehyde is this one, okay? Put a 1 in the chat if so far the color labeling, you're like, okay, that's the aldehyde there. This is the OH that is going to react. Put a 1 in the chat if it's making sense, at least the labeling that I did in the new reaction as we go stepwise, because I don't want to lose anybody in the process. Excellent. So as you can see, this is the Fisher projection of glucose. So the first step into writing that Haworth projection is that you're going to turn the Fisher projection (90 degrees) to the right. And that's what you guys see here. You just make it lay down, okay? So we can see, and I'm just going to color label this so you guys see it. This OH is this OH, okay? This OH is this OH. This OH is this OH. This is the OH that I did in blue. And this group is right here, okay? So in summary, when I take my Fisher projection and I turn it 90 degrees to the side, okay? Basically, anything that is to the right is going to be, so if it's to the right, means that is going to point down, okay? Anything that is on the left is going to point up, okay? Put a 2 in the chat if at least this first step kind of makes sense. We're going to do at least one practice problem so you guys know how to draw the Haworth projection, okay? Good. So in the next step, once I have this structure, understand that now I kind of have to fold it, okay? And in this folding it, you can see that I like to call that this is going to make like a little boat, okay? How do I fold it? So this carbon is this carbon. And you can see how we go from carbon number 1, which is the carbon in the aldehyde, down to carbon number 2, carbon number 3, carbon number 4, carbon number 5, and then this is carbon number 6, okay? From this arrangement to the next one, all we're doing is basically moving the CH2OH to point up. So if we look closely at what's happening between this structure and this structure, basically this group, you can follow the arrow, we're going to move it here. So then we have exposure of the OH, because the OH on carbon 5 is what's going to be interacting with the carbon and the carbonyl in the aldehyde. I think this is where sometimes it's hard to see, but again, we're going to do an example so you guys see it closely, okay? And then in order to do the cyclization, understand that all we're going to do, even though this step, you will be drawing many arrows in order to draw the structure, all I want you guys to understand from the cyclization on the aldol, okay, is that specifically you're going to connect, and I'm just going to do a dotted line, this OH to the carbon in the carbonyl, okay? And then you can see that there's H and OH. This is my aldehyde. The aldehyde is still there. Now, when I make that bond between OH and then the carbon in the carbonyl, this is what's going to happen. Now there is a covalent bond. So that dotted line is this. Okay, so you can see that here it says H and OH. Well, let me erase them and place them in the molecule. Because of the way that specifically that OH can attack that carbon, you can have the OH pointing up and the H pointing down, and this is the carbon in the carbonyl. Okay, if the OH in carbon number 1 is pointing up, this is known as the beta conformation for my monosaccharide. That OH could also be pointing down, okay? Let me just draw the structure for it. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, CH2OH is pointing up, that's carbon 6. When I fill this in at carbon 4, there's an OH down, carbon 3, there's an OH up, carbon 2, there's an OH down. And in this carbon, if the H is pointing up, but the OH is pointing down, this is the alpha configuration, okay, for my monosaccharide, okay? So you can have both being formed. Now, when it comes to this, I want to do a brand new example. Let me just take the molecule of galactose. Let me paste it here, and I can show you guys how we do the we can do it for galactose similarly, okay? So when it comes to this, first I want you guys to identify that this OH is the one that is going to react with the carbonyl. So these two are the ones that are going to react. Step number 1, I'm going to make this turn this molecule sideways, 90 degrees. So remember, anything that is on the right of the molecule is going to be pointing down. Anything that is on the left of the molecule is going to be pointing up. So when I tilt this 90 degrees, I have my C double bond O H or COH, or sorry, CHO. And then let me number the carbons. Maybe this will help. This is carbon number 1. This is 2, 3, 4, 5, 6. So this is carbon number 1. And I have 2, 3, 4, 5. And then the 6th carbon is at the end. Okay. So on carbon number 2, is the OH going to be up or down? Let's put it in the chat. On carbon number 2, is the OH going to be up or down? Thank you for catching that, you guys. I actually wrote up, but it is down. So the OH is going to be pointing down. What about on carbon number 3? Up or down? The OH. Great. OH is up. What about carbon 4? Excellent. What about carbon 5? Great. And remember, whenever you have a monosaccharide opposite from the OH, there's an H. Okay, so this is how we tilt our monosaccharide. Now, remember that I just mentioned to you guys that this forms like a little boat type thing? I always like to say, okay, this is my boat. And in my boat, this is always position 1, position 2, position 3, position 4. In addition to this, I'm going to have carbon number 5. And carbon number 5 is bonded to CH2OH. And that CH2 is actually carbon 6. Okay. Put a 1 in the chat if at least this looks, you know, it makes sense in terms of the labeling. Even if you're at a 1.5 because you're not getting it completely, that's okay. Now, when I start filling this in, the up and down that you see in the tilted fissure will only apply to 4, 3, and 2. Okay? Because in carbon 5, you will see an OH, but that OH must be pointing this way because that's what's going to connect to the carbon in the carbonyl, which is in carbon 1. So this is a C double bond OH. Okay? So then I add my OHs and my hydrogens. So on carbon number 2, my OH is pointing down. On carbon number 3, my OH is pointing up. On carbon number 4, my OH is pointing up. Okay. Now, to cyclize this, remember, all we're going to draw in is a bond between these two overall. And what happens is that this double bond grabs onto that hydrogen, and that's where the OH actually comes from, you guys. So when I draw what's the product of this, there's always going to be 2 molecules. And these two molecules are going to be similar in, and I'm just going to label the carbons in a moment. They're going to look the same on carbon 6, 5, 4, 3, 2. Carbon 1 is going to be different. Okay? Because in one molecule, we're going to have OH pointing up, and the other one, we're going to have OH pointing down. Remember that there's always hydrogens on the other side of the OHs. Now, because when in this class we are doing online, so you guys are not going to be submitting this. I'm just giving you at least an introduction of like, oh, this is how this type of, this is in a way is a condensation reaction. It's just that is a cyclization reaction. Even though you guys are not be submitting drawings like this to me, I want you guys to at least see a little bit of more chemistry happen in this biomolecule. The important thing from this is that if I give you these Haworth projections, that you guys will be able to tell me which one is alpha and which one is beta, okay? So in order to determine alpha and beta configuration, you guys, you will be looking at carbon number 1, always, always. How do I know which one of my Haworth projection is alpha or beta? You will simply look at carbon number 1 and see which way the OH is pointing, okay? So when I look here, my OH is pointing up here, but then it's pointing down right here. So if my OH on carbon number 1 is pointing up, that is a beta conformation in my Haworth. If my OH is pointing down, that is an alpha conformation in my Haworth projection, okay? To make it less confusing to you guys, when I was in grad school, my PhD is actually in carbohydrate chemistry. I came up with this little acronym, which is BUDA. What does BUDA stand for? Beta, up, down, alpha. So if I was given a Haworth projection, I will look at carbon number 1 and look at the OH and be like, oh, OH is up, that's beta. Or, oh, carbon number 1. I can look at this and be like, oh, that's an alpha conformation. So if you remember BUDA, if you're given a Haworth, you will be able to determine if it's alpha or beta. Again, when it comes to the chemistry itself or making the Haworth, at least I wanted to show it to you guys, but understand that for exam purposes, it is important to me that you know the atoms that are involved in the reaction, which you can see that it is the OH in carbon 5, the carbonyl in carbon 1, and lastly, when you make the Haworth projection, determine which one is alpha and which one is beta, okay? That position that I highlighted in green, it is actually, it has a special name. This is called an anomeric position. And it is special because most of the time, whenever there is chemistry happening in a carbohydrate, it's going to happen at the anomeric position, okay? Any questions when it comes to the Haworth projection? Which ones are the atoms that cyclize, or how to determine if a Haworth projection is alpha or beta? Great, then let's move on to the next concept that we need to understand when it comes to reactions of carbohydrates. And that is the formation of a sugar alcohol. So put a 1 in the chat if you have heard of sugar alcohols. Okay, some of you have heard of them. Excellent. So when you Google sugar alcohol, understand that sugar alcohol is not putting sugar in alcohol, okay? A sugar alcohol is an actual chemical. And it is popularized nowadays because it is an alternative to using sugar. So people that have conditions like diabetes sometimes rather use sugar alcohols because in the body, they are not going to technically increase the levels of glucose in the blood just because we cannot derive energy from it. But there are only a few studies that relate to this, but understand that that is one of the reasons why they're used. So how do we form specifically sugar alcohols? Via a reduction reaction. So previously, we learned about oxidations and reductions in organic chemistry, but I'm illustrating here the reaction for a reduction, okay? So when we look at our sugar alcohol, okay, as you can see, if we take a monosaccharide, and you can do this with disaccharides too, if you take a monosaccharide and then it undergoes a reduction reaction, we form the sugar alcohol. So if we go and search for the functional groups that are changed, I want you guys to pay attention to this corner of the molecule. This is an aldehyde. And we learned whenever we were learning about oxidations and reductions that aldehydes, when they undergo reductions, they form primary alcohols. And you can see here, this is the primary alcohol that forms from the reduction of the aldehyde. That is what a sugar alcohol is. Because now the aldehyde is no longer there. The aldehyde motif gets converted into a primary alcohol. So let me just write that as notes. So we go from an aldehyde to a primary alcohol. Now, where do we see sugar alcohols? As you can see, they're used as sweeteners in many sugar-free products. And you can see them in diet drinks. You can see them in sugarless gum. You can see them in drinks. There's actually candy made with sugar alcohols. Now, one of the ways in which we know, in terms of a little bit of nomenclature when it comes to sugar alcohols, that when we take out the OSE ending in our monosaccharide and we replace it with ITOL, then that's how the name of your sugar alcohol is made. So as you can see here, we have D-glucose that when it's reduced, the name of its sugar alcohol is going to be specifically, we take the OSE and we put ITOL. So glucitol is the alcohol that came from glucose. And you can see here in this extra gum that we have something that is called sorbitol. So sorbitol is just another name for glucitol. Okay? So sorbitol, glucitol, same thing. Now, if we look at the ingredients in this sugar-free gum, we can also see that there's another sugar alcohol. It is right here, you guys, mannitol. So if my sugar alcohol is called mannitol, okay, and I'm trying to find the carbohydrate that it came from. All I have to do is replace the ITOL with OSE. So the carbohydrate where mannitol comes from. Any guesses in the chat? What would be the name of it? We replace the ITOL with OSE. Great job, you guys. It's mannose. Let me give you guys a few more examples. Maybe you have heard of xylitol. What is the carbohydrate that xylitol is made from? Excellent, xylose. What about if we have laxitol? Or lactitol is actually the name. Great, that is lactose. Okay, so as you can see, we can go back and forth when it comes to this. I can give you the carbohydrate. Let's say that I give you erythrose. What is the sugar alcohol that is formed from erythrose? Exactly, erythritol. Okay, so when it comes to this, and sorry, there's a delay because I don't see my markings. There you go. Give me one moment. So as you can see, if you're given the name for the carbohydrate, we can derive the sugar alcohol name. And vice versa, if we're given the sugar alcohol name, we can derive what is the carbohydrate. Any questions on sugar alcohols? Then let's move on to the next reaction, which is hydrolysis of carbohydrates. When it comes to the hydrolysis of carbohydrates, understand that hydrolysis, similar to what we learned in the last chapter, is where we are essentially cutting, quote unquote, something with water, okay? So remember that in hydrolysis, since we're breaking down chemical bonds, we need to pay attention of which things can hydrolyze and which ones cannot. In the body, okay, we have enough acid in our stomach to actually perform this hydrolysis. And to be honest with you guys, we are going to actually see in later chapters how hydrolysis actually starts in the mouth, because in biological systems, we have a very specific catalyst that is called an enzyme. So an enzyme is going to be a biocatalyst. And remember that a catalyst just speeds the rate of the reaction by lowering the activation energy. So in the body, not only we have acid present, but also we have enzymes that allow these reactions to happen. So I mentioned to you guys when we start talking about carbohydrates, how we have monosaccharides, we have disaccharides. Oh, great job, Katie. Exactly, amylase. When it comes to disaccharides and polysaccharides, understand that not every one of those type of carbohydrates can undergo hydrolysis. Out of these three types of carbohydrates, understand that only disaccharides and polysaccharides can undergo hydrolysis. So if you have a disaccharide upon hydrolysis, then you're going to make the two monosaccharides that made up that disaccharide. If you have a polysaccharide, then you're going to make many monosaccharide molecules. Okay? So just keep in mind that when it comes to hydrolysis, the only things that can undergo hydrolysis are going to be disaccharides and polysaccharides. Monosaccharides do not undergo hydrolysis. Okay? Now, we saw a few moments ago that our monosaccharides can undergo reduction. Guess what? They can also undergo oxidation. And whenever you have monosaccharides in solution, and this is something that you guys will be exploring in lab, okay? Monosaccharides can actually undergo oxidation. And in this oxidation, because remember, in the structure of a monosaccharide, we specifically have an aldehyde. That aldehyde can be converted to a carboxylic acid. Okay. Now, there is a reagent that is called a Benedict's reagent. In this Benedict's reagent, understand that is based on having a copper molecule. So the Benedict's reagent has a copper 2 molecule. And since it has copper 2, it is blue in color. Now, when you put a monosaccharide that has an aldehyde, or even if it's a ketone, because ketones can be converted to aldehydes in solution, that's specifically in biology. I'm just giving you at least the reference. So when you guys do your experience, you won't be like, but why is the fructose able to do this reaction? Well, there's other chemistries involved, but understand that whenever you have that aldehyde motif in the presence of this Benedict's reagent, it can get oxidized to the carboxylic acid. So since the sugar itself got oxidized, what's going to happen is that that copper 2 is turned into copper 1. So this Cu2O is copper plus 1. Okay? So when this happens, this copper 1 oxide that it is produced in here, it actually has a distinct color. It is a brick red color. Now, understand that whenever you do the Benedict's reaction on any carbohydrate and you see that blue to red transition, that means that we have what is called a reducing sugar. And this reducing sugar specifically is basically, just keep note of it, it's called a reducing sugar. So gives a brick red product in the Benedict's reaction. And the reason why we call it reducing sugar is because the sugar is going to help in the reduction of copper 2 to copper 1. So do not confuse this term and think, oh, if it's a reducing sugar, it means that the sugar got reduced. What this means is that the sugar is helping the reduction of copper 2 to copper 1. The sugar itself in the Benedict's reaction gets oxidized, okay? And this is a common test that it is performed, and understand that when you guys are studying carbohydrates, you will be investigating this, okay? Any questions so far when it comes to cyclization, so the condensation reaction to make a Haworth projection, when it comes to the reduction of sugars, when it comes to the hydrolysis of sugars, or the oxidation of sugars? Great. Since there are no questions, let's move on to the next topic, which this is a topic that I just want to bring up just in case you didn't know about artificial sweeteners, okay? Put a 1 in the chat if you have heard of artificial sweeteners. Great, many of you have heard of artificial sweeteners. What is an artificial sweetener? An artificial sweetener is going to give you, is a molecule that tastes sweet, but it doesn't have the calorie content, meaning that in the body, we don't utilize it to create energy, okay? Now, these chemical compounds are designed to replace sugar in diets by stimulating the receptors on the tongue that detect sweetness, okay? So far we have seen many structures for sugars, okay? So here I have a very small sample of 3 different structures for artificial sweeteners, okay? The one that you see on the far left, that is sucralose, in other words, Splenda. Then on the left, on the right side, on the top, we see aspartame, which is also known as NutraSweet commercially. And in the bottom, we have saccharin, okay? Now, let's put it in the chat. Which one out of these 3 look like a sugar? I agree with Dominique. Splenda. Great job, you guys. For all the people that also put Splenda. Now, it is very interesting that out of all these artificial sweeteners, that's the only one that looks like sugar. And if you actually look at the slogan for Splenda, it says, what is it? Tastes like sugar, but it's not sugar. Let me just look it up. But I think it has something like that. Is it actually in the packet? Let me look. Splenda. What is it that it says on the little packet? No, it's not. No. Or they used to have a slogan of like, tastes like sugar. Or it looks like sugar, but it doesn't. It just says tastes like sugar in the packet. I looked it up. Ah, that's a good one. So this is the thing. What is the difference between sucralose and its cousin, which is a disaccharide, which is sucrose, that we're going to see it in a few moments? chlorines, specifically 1, 2, 3. That's it, you guys. 3 chlorines and boom, we have a Splenda. Now, understand that whenever these artificial sweeteners were created, they were not meant to be used in great quantity. And I don't know about you guys, but maybe you know somebody, you don't have to share this in the chat, of course, but maybe you have gone to Starbucks, and maybe some of you guys, are baristas. It is scary to me when I hear orders of like, can I get blah, blah, blah coffee and then 8 pumps of Splenda? Because for me, as a carbohydrate chemist, it is known what is the sweetness level of these different artificial sweeteners compared to table sugar, which is what we know. That is just sucrose, okay? Now, when we look at the molecules on the right, aspartame, which doesn't even look like a sugar, that is actually made out of 2 amino acids, and you can see them there, aspartic acid and phenylalanine. But hey, it actually tastes sweet. And then saccharin, you look at that molecule, you will never think that that's a sweetener. That looks very, interesting. It has a benzene ring, it has some cyclic structure, but this is what I want to show you guys when it comes to artificial sweeteners. So in the table that we have here, this is the relative sweetness of sugar and some artificial sweeteners, okay? So table sugar is specifically this, sucrose. And that, it was assigned a value of 100, okay? When we look at other monosaccharides, disaccharides, or sugar alcohols, let's notice just a few things. There's only one monosaccharide that is sweeter than table sugar. Let's put it in the chat. What is the monosaccharide that is sweeter than table sugar? Great job. Thank you, guys. Fructose. And as I mentioned to you guys, fructose is in fruit. That's why we love fruit. Like our body knows fructose. It's like whenever you're craving fruit, just because of that sweetness, the body, what is searching is for fructose, okay? And we can utilize it and derive energy from it. Now we can see that all the other monosaccharides, galactose and glucose, are not as sweet as table sugar. Then we're going to talk about their structures in a moment, but lactose, which is milk sugar, or maltose, which is malt sugar, they're not even as sweet as table sugar. When it comes to the sugar alcohols, understand that xylitol is the only one that is as sweet as table sugar, okay? Because xylitol also has a value of 100. But family, look at the artificial sweeteners. And even though it says non-carbohydrate, understand that sucralose is the only one that is carbohydrate derived. The non-carbohydrate only apply to aspartame and saccharin because in the structure, there's not actually a carbohydrate. Sucralose is going to be a carbohydrate derived, okay? But family, let's take a moment and appreciate the sweetness level. Let's start with aspartame. Compared to table sugar, how many times is it? So if we take the 2 zeros and 100, aspartame, like at the base, aspartame, compared to table sugar, how sweet is it? Look, we're comparing 100 to 18,000. That's like 180 times more. Look at saccharin. 450 times more sweet than table sugar. Look at sucralose, 600 times more sweet. Again, as I mentioned a few moments, for me, it's scary when people are just ordering like high amounts, because to be honest with you guys, to date, there's not a lot of data on the effects of artificial sweeteners in health. I think, if I'm not mistaken, from other colleagues that I collaborate with, there was a study done specifically in mouse models. Mouse and other rodents sometimes are used as a model system for how maybe the effects are in our body, just because at the genetic level, we're very similar in terms of a human and a rodent. So understand that's why it's used. But it was suggested that when it comes to utilizing artificial sweeteners, instead of them helping control blood glucose levels and people being able to enjoy some sweet treats, if it's used at certain levels, the artificial sweeteners have been detected to be toxic to important organs like liver, like kidneys. Okay. Again, consumption of this and the levels of it affected, right? Like if you're having this for years and years and years and years, exposure to this in high level, understand that it may affect your health. But at least in mouse models, they saw that the kidneys and the liver of these rodents were being affected by the use of artificial sweeteners in high levels. And you may think like, oh, but people cannot use it in high levels. There are people that this is their norm. Eating a lot of Splenda, eating a lot of aspartame, eating a lot of saccharin, okay? Just because they think it's like, oh, this is good for me because I still get the sweetness, but then there's no calories. Another thing that has been observed, and this was more recent, that for people that are diabetic, even the use of artificial sweeteners were spiking their blood glucose level. And that is a little bit more concerning, just because you're trying not to have that because you already have diabetes. And if these artificial sweeteners that are supposed to help you are, again, affecting your blood glucose levels, that can be a concern. So just be aware of the realities of artificial sweeteners. I'm not going to tell you to eat them or not eat them, but at least understand that they are way sweeter than table sugar, okay? Now, we are going to finish up talking about the other types of carbohydrates that I mentioned when we started talking about carbohydrates, starting with disaccharides. As I just mentioned a few moments ago, first, we're going to talk about maltose. Let me specify to you guys that when it comes to the exam, it is important that you know the different monosaccharides that make the disaccharide, and specifically how they're linked to one another to give the disaccharide. So when it comes to maltose, also known as malt sugar, which is found in cereals, is found in candy, and it is actually the preferred sugar when it comes to brewing. This is actually what I studied when I was in Canada. We were understanding how is it that yeast knows which sugar you have fed it, but it's all biochemistry. It's a beautiful thing that the yeast actually remembers if you fed it of one sugar versus another because of the biochemical pathways that it activates, even though yeast doesn't have brains. But anyways, I'll talk about that, at some point, maybe later. But understand that when it comes to maltose, we can see that maltose comes from an alpha D glucose reacting with an alpha D glucose. These two alpha D glucose molecules are going to undergo a condensation reaction. And in this condensation reaction, we're going to have that disaccharide. Now understand that the link between the two monosaccharides, that is called a glycosidic bond. And specifically for maltose is going to be an alpha 1,4 glycosidic bond. Now, because the glucose on the right of the molecule has an anomeric position here, okay, we can have an alpha maltose, but we can also have a beta maltose. Well, you can see illustrated here the alpha maltose, because again, since this is carbon number 1 and the OH is pointing down, that's why this is the alpha version of maltose. If the OH is pointing up, same structure, but then the OH is pointing up, that's going to be beta maltose. Now, when it comes to lactose, which is milk sugar, and understand that lactose is formed by the monosaccharides beta D-galactose and alpha D-glucose. Overall, we also have a glycosidic bond, and the glycosidic bond here is an alpha 1,4 glycosidic bond. Remember, glycosidic because it's linking two sugars. So we have a galactose and a glucose molecule coming together and making this lactose. Understand that lactose, okay, since it's found in milk products, not all milk products are going to have the same amount of lactose, because as you can see, human milk and cow's milk have different amount of lactose, and based on that, the sweetness levels for them will be different. But similar to what we saw in lactose, okay, or sorry, in maltose, since lactose has an anomeric position where we can have OH point down or OH pointing up, here we're illustrating the alpha isomer for lactose. We can also have beta lactose. Lastly, we have table sugar. And table sugar is going to be sucrose. We can see, or we can obtain sucrose from sugarcane or even sugar beets. Now, when it comes to what are the monosaccharides that make table sugar, you can see that the sucrose comes from alpha D glucose and beta D fructose coming together. Now, these two monosaccharides are linked to one another via the connection of their anomeric positions in an alpha beta 1,2 glycosidic bond. So now, because in sucrose, the anomeric positions of both monosaccharides is what links them together in this glycosidic bond, understand that sucrose is a non-reducing sugar because it doesn't have an alpha beta isomer that can be oxidized in a Benedict's reaction, okay? Lastly, to conclude our conversations about carbohydrates, here we have polysaccharides, okay? Now, the polysaccharides that you see here, we can observe that all of them are made out of glucose. So the subunit, this is going to be the monosaccharide that they're made from, okay? And all of the polysaccharides that we see here are glucose-based, okay? Now, we can see that some of them have branches, some of them don't have branches. And to quickly explain the difference between them, we can see in the first column in orange, cellulose as a polysaccharide. So glucose or beta glucose is going to be what makes this molecule. And we can see the shape of it in the last row, okay? Now, cellulose, it is not branched, meaning that you don't have glucose coming out the main chain. So that's why you see the shape that it is. When it comes to starch, so whenever you're consuming pasta, potatoes, even some beans, and it has starch in it, understand that there are two polysaccharides that make starch, amylose and amylopectin. The difference between the two is that amylopectin is branch, but amylose is not branch. And you can see it in the shapes in the bottom. Also, the connectivity of the bonds between the subunits or the monosaccharides is going to be a little bit different because they have alpha 1,4, and because amylopectin is branch, the branches are 1,6. So this is specifically for the branches. Give me a moment because this stopped getting connected. Let me see if now it will connect. Let me see if it will connect now. To be honest with you guys, I'm having connectivity problems. My iPad doesn't want to connect to Zoom and it's already 7:23. So I'm going to, on Thursday, finish up with the polysaccharides, the carbohydrates that we have in blood, and then we're going to start chapter 7. So thank you guys so much for coming today.